Hi there, and welcome to High Performance JavaScript, and I'll be walking you through some of the ways that we can utilize our JavaScript to improve both the performance and the experience of our web apps, both on desktop and mobile applications. As we get started, we'll be using a variety of tools for both benchmarking and profiling our code and the experience overall. These will include some tools such as Chrome profiling tools, which allow us to see the full web page both as it renders for the user as well as how Chrome and various browsers themselves parse through that web page, anywhere from the various ways that we load our various scripts, which could be one at a time if we've concatenated them all together, or several microscripts that are all relatively small in size. Profiling tools also then give us insight into how the browser actually renders and displays that information for the user. This includes the DOM paint flow, the various reflows that happen as new information comes in, either from dynamic data or AJAX calls, or possibly just as we've loaded more of an image or CSS files and other sorts of assets. It'll also allow us to dive into what happens as the user begins to interact, when they click on buttons or start to fill out form fields, or even just as they scroll down the page. What is it that the browser handles seamlessly? What aspects slow down the way the browser is able to render and respond to the user that could give our end user a less than optimal experience? Additionally, we'll take a look at some tools that give us targeted optimizations. These include options like JSPerf and Benchmark.js that allow you to take small snippets of code and run them thousands or even tens of thousands of times with micro variations, understand which variation works best for your specific scenario. Those micro optimizations are best for raw speed, so it's in that section where we'll focus purely on code-based optimizations. These could be different ways to construct your loops, to making sure any variable you use is only allocated as much memory as it needs and no more, and then of course that we're assisting the garbage collection in any way that we can. We'll also look at frameworks such as ASM.JS, which is a subset of JavaScript designed to compile even more optimally into the C-based parsing that Chrome and other browsers utilize within the V8 engine, as well as other JavaScript engines utilized in Firefox, Internet Explorer, and browsers as a whole. For these, we'll be focused primarily on the micro optimizations and less so on the total flow, including browser paints, the way a rendering engine actually puts everything together, etc. Next, we'll move on to that browser flow. These will include a lot of browser-specific updates where the changes we make will help out Chrome, but either be worthless in Firefox or might even make Firefox worse. For those instances, we'll have to balance out to make sure that we have the best optimal experience for everyone, and more specifically for our target market. If we know that everyone in our user base is primarily using either Chrome or Firefox, we can disregard a lot of quirks and hacks that we have to do for Internet Explorer. Much of this optimization will come from understanding the DOM paint flow and reflow process. This is the process by which the browser takes the HTML, the CSS, and then any extra data or updates that JavaScript provides and flows it all together to produce what you actually see on your screen. The initial flow is pretty straightforward and much of it happens as you might imagine it. However, the reflow process, which is what happens anytime someone scrolls, something in the DOM changes, such as a menu appearing or some data being swapped out, or even just something as simple as a carousel rotating through different images. These are all part of the reflow process, and how we structure it together and how we change that data determines how much rethinking, so to speak, that the browser has to do, understand what parts of the page need to move around and which parts remain exactly as they were before. Another way that we'll utilize this is looking at the shadow DOM, which is a new concept that allows us to have basically a virtual copy of the DOM that doesn't get affected at all by this reflow process. This allows us to make several manipulations and change significant pieces of the DOM without getting hung up in that paint flow process, and allows us to then simply swap out one DOM, the shadow DOM, right into place for the original DOM, allowing us to make all those changes in one seamless reflow, as opposed to having several incremental changes that can build up and cause latency. Finally, we'll take a look at some of the advantages or disadvantages of making visual updates via CSS versus JavaScript. Sometimes it's helpful to just change a couple properties via JavaScript, and that's often the simplest way. However, the browser was built and understood CSS far before it understood JavaScript. So much of its rendering engines are better optimized for CSS-based changes rather than JavaScript and actual DOM manipulation changes. We'll see this most specifically when it comes to showing or hiding several pieces of data, such as thousands of items in a list or something that you might search and filter through based on various different expressions. Additionally, we'll take a look at some of the ways that you can target your CSS to make it even more optimal, such as making sure that the class you use to change things is on the nearest parent possible to what changes, Because any tag that goes on the body, the browser is forced to reflow the entire document to understand what might have changed, even if really it only affected one or two paragraph elements. Next, we'll take a look at some user experience enhancements. And these are things that, from the browser's point of view, really don't speed anything up at all. However, from the user experience perspective, significant improvements can be made. These include things like, do you want to include a loader or not? Various studies have shown that sometimes including a loader helps the user know that something is in fact happening and their browser didn't just hang on them. But if the wait would have been small enough, simply adding the loader tells the user that there is a wait, and they actually notice that delay, and that makes the delay feel even longer for them. Additionally, we'll talk about things like assumed success, which is the concept of any time you make an API call or a change to some data, or really are responding to the user's interaction in any way, you want to assume that it would have worked and render it immediately, if possible, as that change would have occurred. This can be things like when you're making an inline change and they click save, immediately rendering the now static view of that data as if it had changed, which then allows the user to go along, and of course, hopefully, assuming your API is constructed well over 99% of the time, that success will in fact have occurred, and there was no reason for us to make the user wait. Only if there's an error do we want to bring that back to their attention. You've likely seen this in situations such as Gmail's compose message, where as soon as you click send, the little compose box disappears and you can get along with the rest of your email. And it's only if, for some reason, that send fails that the compose pops back up and it displays an error about what's happened. Another aspect of user experience enhancements comes from utilizing preloading and incremental updates. Perhaps the most prominent example of preloading again comes from Google, where at one point they added the ability that as soon as you hovered over a search result, in the background it would start loading that page for you. That meant that as soon as you clicked it, because at least half the page had already loaded, it felt faster, which made your entire experience with Google and their search results feel significantly faster, even though really nothing in the code itself had actually changed. This was a huge user experience improvement, and even though most users would have never cognitively recognized it, it made them enjoy Google more and therefore utilize it more over other possible search engines. We'll look at examples like that for preloading, or possibly simply images, or based on your user's usual target flow and the way they navigate through your app, simply preloading views as they get closer to that time. We'll also take a look at utilizing local storage and AppCache to help make sure that anytime there's an online-offline situation, such as the network cutting in and out, or possibly just an app that your users come to hopefully daily, maybe even several times a day, the vast majority of the assets and code that they need to utilize it are already there and ready for them, stored on their computer, potentially even storing some of their own data, as much as we can securely allow them to store, thus making sure that the moment they want to use your app, it's already ready for them, and it only has to check for any new updates or incremental changes once it's already loaded. Finally, we'll take a look at some mobile enhancements. These are changes that specifically apply to either mobile or tablet browsers or situations where the network is significantly poorer than we're usually used to. These can again include very browser-specific things, such as for Android or iOS. We'll also look at methods for lazy loading and only loading conditional assets based on the browser that's actually requesting our page or our application. We'll take a look at different methods for handling those online-offline changes. Again, some of these are as simple as utilizing local storage. Some of them are simply notifying the user as soon as they've gone offline to let them know that all their changes are going to be stored but won't actually be persisted until they once again reconnect to the network. That was just a quick overview of what we'll be covering over the next several stages and chapters. Next, we'll move on to take a deeper look into some of those tools that we mentioned to get a good feel and comfort level for them before we go on to the actual optimizations. As we get started, we're going to look at a few different profiling and benchmarking tools that we'll be using throughout the course just to get familiar with them and give you a quick overview. At various points during this course, we will dive more deeply into specific aspects of each of these tools, but we want to do a quick overview first just to get you familiar. We'll start with some of the profiling tools in Chrome dedicated to network debugging and benchmarking. First, we have our Resource Timing API. This allows us to dive into specific aspects of each call and load of whether it's an asset or an AJAX call or anything else like that. You can see here that if we open up the console in Chrome, we can find on window.performance this getEntries method, which returns an entire array of items just like this one, each of which corresponding to a specific asset or resource. There are obviously other methods on window.performance, and they all correspond to the spec specified here on w3.org, which you're welcome to dive into more, and we'll review a little bit as we go forward. The important part to know is that it provides a microsecond level timing information, so it's highly accurate. And it gives us items such as connection start, end, and duration, any steps, whether that's redirects, DNS resolution, etc., as well as the impact of SSL or HTTPS versus regular HTTP downloads. We can also use it to filter by different types of resources, so whether it's an image or a CSS or JavaScript file, or potentially something loaded via an AJAX call. And all of those resources will be helpful as we're trying to benchmark and improve and optimize our downloads and initial load of the page, as well as any further data changes that we make. Next, we have the Network tab. You've likely seen this already. It's a pretty high-level view of all the downloads that come through and any data that's uploaded or downloaded from any variety of servers. One of the most important things to remember with the Network tab is that it doesn't start recording and making note of all the different downloads until the Network tab, or at least Chrome Developer Tools, is actually up. If you've opened it after you've loaded the page, you'll need to do a full reload just to make sure that you actually see all the resources. Another important thing is this item at the top called Disable Cache. It's a quick way for while you're doing your development to toggle the cache on and off so that you can easily see either a first time load experience or second or later time load experience depending on what you're trying to optimize. Some of the advantages of the Network tab is you can easily sort by duration, load order, etc., and it provides a variety of filters to allow you to drill down specific ones. This sorting gives us the ability for quick hits so we can see which assets take the longest to load, which ones, if any, are blocking later loads, etc. We're also able to filter by a huge variety of items. You can see here that we focus just on MIME type, allowing us to dig into the text/JavaScript files that are downloaded based on that MIME type. In this case, that's very similar to simply selecting the script filter at the very top. But these filters in the search box allow us to add on and combine different filters to pinpoint the exact items that we want to look at. The other important network tool inside Chrome Profiling Tools is this timing tab. What this is on each individual asset that gets loaded, we're able to look at the timing, see how long a connection was stalled, when the request was sent, how long we were waiting to hear back from the server or time to first byte, and then how long it actually took us to download whatever the asset actually was. This tab is a quick high-level view for each individual resource, but if we want to get into more detail, we'll want to go into the timeline tab, which is what we'll look at next. For those times when we want to dive even deeper into the intricacies of the timeline and the way the browser both receives data, whether it's from a network or user input, as well as how it responds to various inputs and interactions, something as simple as a scroll or a mouse moving, or as much as clicking a button, reflowing the DOM, or any sort of visual changes that take place on the screen. For those instances, we want to use the Timeline tab. The Timeline tab holds a wealth of information, and for this video, we're simply going to do an overview to give you an introduction to all the different areas and what they generally cover. We'll go into more details in some of the upcoming videos as we focus on specific aspects of each tab and each view that it presents us. Here's the Timeline tab overall. The first thing to know is before we can actually utilize the Timeline tab, we have to use this Start-Stop Recording button at the top left. What this means is much like with the Network tab, where things don't just automatically show up here, we have to be explicit and go into the Timeline tab, hit the record button, and then reload the page. You can also record just a simple segment if all you want to focus on is a specific interaction or animation or some sort of dynamic load, but in most cases you're going to want, at least at the beginning, an overall page load to understand what happens when the user first hits your site or first loads a specific view. Once we have the view where we want it, we'll click that record button again to stop the recording, and Chrome will go ahead and parse through all that data and present this kind of view. You can see here in the Summary tab that it's broken down not only our entire range of just how long we were recording, but then how much of that time was spent loading assets, how much of that time was spent processing a script, how much of that time was spent rendering or understanding based on the script, the CSS, the DOM itself, where everything should sit, and then finally how much time should be spent actually painting that rendering, or rather coloring each individual pixel in the appropriate area. This view, as we have it right now, is not very useful to us because it's a full 13 seconds of load and various processing. We can't really drill down and understand what's happening. So for that, the Timeline tab provides zooming. You can see here, if you look at the range, that you can see we're at only 0.04 of a span, and that includes us parsing the HTML, evaluating a script, in this case it looks like it's coming from an extension, various different anonymous functions inside, as well as other functions that get called out throughout. Just as we saw on the overall view, we still have it broken down into loading, scripting, or any sort of other processing that Chrome has to actually handle. While this zoom is handy, oftentimes when we really want to optimize, we're going to be looking at specific steps. And what this is you can click into Evaluate Script and see just how long this specific segment took to run, where the script originally sits or was loaded from, as well as yet another breakdown of the processing time within this specific function or processing time spent on functions that were called out to. Not only can we handle specific steps though, we can also take a look at specific events. This allows us to drill into what the browser is doing and handling every time there's any sort of event, whether it's a mouse move, as you can see in this instance, or it could be something like a scrolling, again, input via a keyboard or a button, or any other sort of interaction that the user might have with your site, or potentially even interactions that come from background data loading. Once again, we can see here we have a multitude of mouse move events, each of which call out a specific function. In this case, it's only 0.005 milliseconds, so that's obviously highly optimal and really not something we need to worry about. But it's always good to be aware, specifically for high trigger events such as mouse move or scroll that tend to fire off tens, if not hundreds or thousands of events during what a user considers to be simply a single action. Those events in particular are easy to build up and cause some of the sluggishness and drag and delays that we can feel with what we would call bloated apps. And then finally, the last thing we want to cover with the timeline tab is the painting section. This is where the browser is actually coloring in the screen based on what it's rendering from the HTML, CSS, and JavaScript. You can see here that the Chrome timeline tool allows you to really dig into each individual moment. Inside the rasterized paint, we have a matrix setting, clipping of a rectangle, drawing of a rectangle, each individual rasterizing, and even image decoding. At this point, we're simply going to leave it at that. However, realize that when we get into the sections on browser flow and reflow, as well as some of those elements on scroll, this is a tab where we're going to spend a lot of time because it's the painting that happens in those instances that is often the slowest part of actually displaying our information to the user, as well as something that if you pay attention and know a couple good tricks can be pretty highly optimized. As we move on into the next section on raw speed and code optimizations, we'll do a quick overview of some of the inline code performance tools like JS and Benchmark.js that we'll be using, and then we'll dig into them as we go to just understand each individual piece as we need it. For this video, we're going to be talking about some micro optimizations that you can make for both loops as well as for variable and property scoping as you execute methods either within a loop or simply other functions that are frequently executed several times during the duration of your app's usage. To do that, we'll be using JSPerf.com. If you haven't used it before, it's an easy way to test multiple different iterations of code or variations within that code to understand which ones perform the best, and you can even publish them so you can easily test them in various different browsers so you understand not only how it works in your own browser, but also the common breakdown of your users' browsers. To set up a test, simply go to JSPerf.com, fill out your name and email, and then go ahead and create the test. For that, we use a title, slug. You can optionally publish it or leave it private if you want to make a few changes before showing it to the world. And then once we're ready, we simply insert some preparation code, which allows us to include whether script libraries or any sort of other assets that we might be using. And this preparation code HTML is only run once. Again, you can load either your own script tags or some basic script tags for global initialization. But most of the time, what you really want to do is use this setup, which allows us to initialize some variables, some data, whatever we might use for each individual test run. And this, of course, will be run at the beginning of every test run to make sure that we always have the same starting place. Additionally, if you want, you can also define some teardown for your test in case there's any global variables that you want to reset when you're done before moving on to the next iteration. Once you're there, you can create as many code snippets as you want with a simple title, as well as the code itself that needs to be executed. There is the option to do some asynchronous testing, which we'll look at later, but for our purposes today, all our tests will be synchronous, so we won't worry about that right now. The main thing to remember is that all of the code that's run here is executed through Benchmark.js, which is a common JavaScript benchmarking framework that allows us to test our code either in the browsers we're going to do here, or optionally also in something like Node or other server-side setups, and see how it performs in all sorts of environments. With that set up, we'll go ahead and take a look at our first test. You can see here that my setup code is pretty straightforward. I'm defining an empty array of items and then looping through 0 through 10,000 and just adding those numbers to the items array. We'll use this items array within our code to help us understand how loops are running and functioning, but we don't actually care about the specific data that's inside it. Next, we have this global variable sum, as well as a function that adds whatever number gets passed in to the sum and returns the now updated sum. For this test, all we're really doing is checking to see if there's a most optimal way to loop through all the numbers inside items and add them all together to produce one final sum. For that, we've started with the standard control, which is exactly how you've seen the for loop almost always demonstrated. We initialize an I to 0, our break expression, or the expression of I less than items.length, which must always evaluate to true in order for the loop to continue, and then I++ to increment it as we go forward. Once inside it, all we do is call add to sum with whatever value resides at the index I of items. And then once we're all done, we call console.debug with our final sum. For our second instance, we are caching the total length of the items. This makes sure that we don't have to check it every single time we evaluate that break expression, or in this case, 10,000 times. For that, we've stored it as I, and then our break expression is simply I less than I. This is a pretty standard optimization. As you can see here, we've gained a little bit from it. If you look at the right, we got just over 3,000 ops per second as opposed to 2,800. However, this is a pretty micro optimization, and honestly, if you reran this test 100 times, probably 60% of the time caching it would come out faster. So it's really not something that we need to focus on a lot, and most of the time doesn't matter unless your items is an extremely large array. One of the other most common optimizations is to run it in reverse. This essentially has the exact same advantage of caching the length because we only have to check it once, and after that we're simply counting down. Naturally, this means we're looping through our array in reverse, so if that matters to you and the exact order is important, this is out. And you can see that on this specific run, it actually ended up even slower. Again, it could probably come out at about the same as our standard control. The next three items here are just your standard while loop along with explicit increment and decrement. While loop again is going to run in reverse and again is still about the same. Both explicit increment and decrement are designed so that instead of using the I++ or I-, we're explicitly adding it. This has the advantage of not having to temporarily redeclare a variable for I, which is the way a standard JavaScript parser handles those increment and decrement operators. You can see on the whole, almost all of these are very similar, and this is because in modern browsers such as Chrome that we have here, they're so highly optimized to handle loops like this that there's really not a lot of optimizations we can do on the standard run. All the old tricks that you had from 2 or 3 years ago, where this spread would have been significantly wider, have pretty much been narrowed and fully optimized. That said, there's a lot of new loop types and methods that you can use for looping, and those are not nearly as optimal. For this, you can see we've got the exact same setup, and our initial control for loop is still exactly the same. However, we're going to take a look at a couple other ways to loop through an array and see how they perform. Our next option is the for of loop, in which case, instead of using the standard I = 0 break expression of less than items.length and then an incrementer, we're simply telling the browser to increment through each of the values in items. As you can see over on the right, it's exceptionally slower, about 1/10 the speed of our standard for loop. The same holds true for our for in loop, which ends up being the absolute worst. The other important thing to note is that for in does not have a designated order, and so the properties that you receive, or the indices in this case, could appear in any order and at random. There's no guarantee across browsers or even within the same browser. One of the newest additions to the JavaScript parser is this .forEach, which accepts an iterator function. In this case, it receives both the element itself and then the index of the element if we wanted it. This is significantly faster than for of and for in, but is still less than half the speed of our standard for loop. Simply for comparison, I've brought the while loop back, which you can still see is virtually identical in speed to our original for loop. With that in mind, it's important to realize that most of the optimizations you're going to do regarding loops and iterating over various arrays and objects is not going to come in caching a break expression value or traveling it in reverse and changing the way your incrementer is displayed, but rather it's going to have to do with what you actually do inside that loop. And so with that in mind, let's take a look at scoping. Now, what you may or may not already know is that the way JavaScript finds a variable when you ask for it follows a specific pattern. First, it looks for this. If your variable isn't this, that won't really matter. Next, it's going to look at local variables. So these are going to be their variables that are defined inside the same function that's currently running. After that, it looks at the variables that were passed to the function. So these are going to be whatever parameters your function defines and expects. After that, it continues to go up one by one in the scoping level. So if you have multiple closures, it'll continue to traverse that tree until it finally hits the global scope. You want to make sure that any variable, whether it's a property or a method, that you need to use several times over, you want it defined or scoped as closely to the code that will actually be executing it as possible. So for this setup, we still have the same items array and a function for add to sum. But we've also gone ahead and created this utils object or utilities, which is something that we commonly use inside our code when we have a variety of libraries or services and factories that we might be depending on throughout our entire application code. So you can see that this object utils has a single property math and then one method add to sum. Likely both math itself as well as the entire utilities object would contain significantly more items, but in this case, for simplicity, this is all we'll use. Once inside, we still have our control for loop, which is identical to the ones we've seen before. For our next one, however, we've gone ahead and reassigned that global add to sum function to our own individual sum function and then used that within the loop. You can see that in this case, because our test code is so close to the global scope already, we don't actually gain that much. And in this case, we've actually lost a few hundred operations per second. But again, if we ran this 50 times, it would probably be about 50-50 on whether this or the control is faster. Notice, however, what happens when we get into our next test case, where instead of calling the global add to sum method, we're drilling down into utilities.math.add-to-sum. In this case, we're nearly 50% slower, running at almost half the speed of what it originally was. And that's because it has to traverse down that object to find the add to sum method. If instead, as you can see in our final option, we cache that function, we only look it up once and store it again as sum fn, and then call that within our loop, we return pretty much entirely to our original speed, which allows us to have the advantage of namespaced methods and properties without having to lose any performance when we actually do our executed code. Finally, as one last example of understanding scoped properties and caching things that we might retrieve off an object or service, let's again take a look at this. But this time, instead of caching a function, we're going to cache a property. So our sum variable, instead of being global, is now just one property inside data inside our entire application object. For our control function, rather than caching it, we simply drill down each time and then add the value. However, if we use a temporary variable, we're able to almost double our speed. This demonstrates one of the most important philosophies when it comes to optimizing your code. You want to write the code first and then do your optimizations. Often when you get into the concept of optimizing code, it's easy to think that if I just used a different type of loop, whether it's the for with a decrementing operator or ran it in reverse or used a while loop instead, and just had that as a constant pattern, then all my code would be optimal. But as we saw at the beginning, those micro changes make almost no difference, particularly in modern browsers. However, if after you write your code, you realize that a particular method or property is going to be used hundreds, if not thousands of times within a particular execution run, and that property or method is far away from a scoping perspective from the code that's actually running, you can use that opportunity to create a temporary variable or cache some sort of data and execute upon that, which will give you far greater improvements in your overall optimizations than if you simply focused on some of the small changes that we looked at in that first original test. For this video, we're going to be talking about ASM.JS, what it is, why you might want to use it, and if you're interested, how to get started. We will be doing a pretty high level and quick overview because, as you'll quickly see, some of the development overhead to utilizing ASM.JS is very high, and it really only has a few kind of specific areas of use at the moment, but it is something that's worth knowing about and having a good understanding of, at least from a high level perspective, so you can help make that decision of whether or not it's applicable for your particular application. ASM.JS is a very specific subset of JavaScript that's designed to be highly optimized. And what this means is that Mozilla, the company behind the development of ASM.JS, has severely limited what you're allowed to do inside ASM.JS to make sure that the compilers in the browser, when it's processing it, has to make as few assumptions as possible. This allows it to execute significantly more quickly and more highly optimized in a manner that's much more efficient, particularly for calculation. However, it is still all regular JavaScript, so it is 100% backwards compatible. For ASM supporting browsers, it does go ahead and compile ahead of time based off a Prolog directive that we'll look at in a moment. In those supporting browsers, we do currently get within a factor of 2 compared to the performance of native code, which is several factors higher than standard JavaScript parsing. One of the most important things to know about ASM is that it's never intended to really be written directly. Because of the high level of requirements and limitations around it, far more commonly you'll actually be writing either C or C++ and then running that code through some sort of conversion process to output the actual ASM.JS. Before we even dive into how to get started though, it's important to consider when to use it. Because of the high level of overhead, such as originally writing it in C or C++, some of the additional headaches just when trying to do any sort of debugging because you're multiple steps removed from the code you're actually writing to what the browser is parsing, it's really not necessary or practical for standard web apps. However, if what you're building is a game or some sort of computational heavy application, such as a port from desktop software or any sort of statistical or analytical program, ASM.JS can be a huge performance bump for your overall application, particularly in specific areas. So if you decide that there are particular pieces of your application that you want to use ASM.JS for, the easiest way to get started is just to head over to asmjs.org and first review the spec and FAQs and make sure that you really understand what is going to take to get involved in this, because like I said, that initial development overhead can be relatively high. However, one of the advantages of the way ASM.JS has been built is that you don't have to convert your entire application. Something as narrowly focused as a single file or even a single function can be scoped as ASM so that the browser knows to compile just that single bit and allow the rest of your application to still be in normal JavaScript that you've written already. So it is possible to kind of piecemeal, improve, and slowly convert your code over, only optimizing and really putting in the extra time on the specific functions or methods that require the most optimization. After that, you obviously have to then write the code in the C or C++ and then utilize a converter, one of the most popular of which is currently Emscripten. And then you just embed that converted JavaScript. And to embed that JavaScript, we simply use, in quotes, use ASM, semicolon, just like we see use strict all the time when we want a more strict parsing of our JavaScript. After that, we follow the same process that we've seen 100 times of test, optimize, and repeat. But of course, you have to make sure that these tools are running in ASM-compatible browsers and that they're actually doing that compilation. Otherwise, you're simply comparing JavaScript to JavaScript. At this point, you may be thinking, why then, given the extreme overhead of actually trying to do some of this development, would I even bother? The truth is, for applications where the code is optimal to be converted, and again is something that's either highly computational or requires significant algorithms, the performance can be huge. Here's a graph from some of the original ASM presentations, and you can see here these are 3 different libraries that are all standard software libraries used on desktop, both run as standard JavaScript or with Firefox and ASM enabled. And you can see, comparatively to the standard JavaScript, we're talking orders of 5 to 10 times faster than the standard JavaScript. Obviously, it's still not quite native, but comparatively to the rest of browser speed, this is a significant leap forwards. While the development overhead is huge, and like I said, for most standard web applications, it's really not worth the investment. If you do have an app, such as a game or any other sort of software that requires a lot of computational processing, I highly recommend you dig in and evaluate whether or not the investment is worth it for you. For this video, we're going to be talking about utilizing web workers to help offload some of our main processing and help balance out that processing across multiple threads, particularly on multiple core machines. If you're not familiar, a web workers is a new technology introduced into browsers to allow us to offload or utilize separate threads for various different background processing. They allow us to break out of some of the restrictions usually imposed by single-threaded JavaScript. However, they do have a different set of restrictions all on their own. Most notably, web workers are not allowed to directly interact with the DOM, and instead they communicate with the main thread via messaging, both receiving and sending those messages. This ensures that you never have to introduce any sort of locking on a particular DOM element or other techniques to ensure that different threads aren't trying to edit the same DOM element at the same time. To get a quick introduction then, we'll take a look at a very simple example of trying to calculate a random calculation, something that might be seen as computationally intensive, both via a standard method, that is just calculating it all on the main thread, or utilizing workers, where we'll create a couple different workers and we'll send out different pieces of that calculation to each worker and then aggregate the result. So you can see here in our HTML, it's pretty standard, just an input where we choose what number we're going to use as our basis for the calculation. A couple different buttons depending on whether we want to use our control or the workers, and then a few simple paragraph tags to display the statistics for how we've done in each case. For our JavaScript then, all we've done is collected the various DOM elements that we're going to want to update. We have this standard calc function, which takes a number, gets the square root of it, drops it by 1, and then adds the square root of the next number, and so on and so forth, all the way down until we hit 0. Our control button simply again does it purely in the main thread, as you can see right here. Our new technology, the web workers, are all inside this workers button. We initialize everything basically the same, except we're creating this buffer value, which tells us what range of numbers we want to apply to each worker. In this case, you can see we're going to create 10 workers and then divvy up the numbers you can see here. We'll return to this handler in a moment, but first let's move down to the loop. We create a worker, and the way creating a worker works is you use this constructor, new worker, and then you point it at the JavaScript file you want to load into that worker. Unlike what you might be familiar with other languages, JavaScript workers in this multi-threading concept focuses entirely on its own set of files. You can't simply create a function and ask it to run that function off on its own thread. So we point it at the file that we want to load, and then we calculate the data that we're going to send. And then we use this onMessage property to attach the handler. Now, onMessage is a callback that will get executed anytime the worker tries to send a message back to the main thread. And then on the next line, we do the reverse. Every worker has this postMessage method, which allows us to send data into the worker. In a moment, we'll take a look at how the handlers in this messaging are implemented on the worker side as well. One key thing to be aware of is that sending data back and forth between workers is not the same as just sharing data across functions like you might within a single JavaScript thread. Most notably, objects are always passed by value, never by reference. What this means is that if you send an object through and then you change a couple properties, the object in the main thread will never reflect that change unless you send it back and inform the main thread. The simplest way to imagine it is simply assume that you're taking all your data, serializing it to JSON, and then unserializing it back from JSON into JavaScript objects on the other side. There are a few changes that make that not exactly true, but by and large, that's a good way to think about it when you're sending data back and forth. Before we move on to our worker file, let's just take a quick look at the handler then. You can see that the handler receives two arguments. First, the event, which contains the data and a few other properties, and then the worker itself. In this case, we want to retrieve the data as a float, since we're aggregating the results from all our different workers. And then we want to remove that worker out of our buffer or our queue to let us know that it's already done. And then once all our workers have been removed from the queue, we can mark it off as being done and update the total. So what does our worker look like then? Here's the worker file. You can see that our calc function is almost exactly the same, except that we're using a range rather than simply a number till 0. Notice here that we've created this onMessage function, and we appear to have violated the number one rule of JavaScript, which is storing this on the global object. However, in the case of workers, the global object is not actually the window itself, because remember, we don't have access to the DOM from this worker. Instead, this is what's called the global worker object. And by defining this onMessage globally, that actually creates the handler for any time data is sent into our worker. So you can see here, this is in fact exactly how we receive that range of data that our main thread has sent through. Similarly, once we're done, we simply call this method postMessage, even though that's not defined anywhere. Because just like we wanted to define onMessage on the global message object, we also want to utilize postMessage, which is already defined on the global message object, to send data back. So let's go ahead and take a look at how that renders in the browser. So you can see here, we're just going to calculate our square root sum. We're starting with 100,000. We do it with the standard method. It's pretty fast, 2 milliseconds. However, if we come over and use our workers, we can see that, not necessarily what we were expecting. And this is a good example of making sure that when you're learning about all these different ways to optimize and improve your JavaScript, you actually make sure that the technology you're picking or the optimization you're picking is valid for your particular instance. Web workers have a lot of value, and we'll look at a couple different ways here in a minute, but it's important to know that they're not free, and threading is still very early on in JavaScript, and so there's some inefficiencies here. We can actually make this a little bit more efficient if we change our number from 10 workers to 2. When we reload the page, we can get us down to 50 milliseconds instead of over 200. But still, that's pretty inefficient compared to what we saw previously, which is the standard run of about 1 millisecond in this case. If workers aren't necessarily great for just offloading a single calculation, what are they good for? Well, there's a multitude of uses, and really you'll need to know your own web app to understand whether or not they're a good instance. But some of the most common things are background data, polling, or any other sort where you want to take a result and slowly migrate it across your entire application without forcing your main thread to be focused on it. Really, a good way to think of web workers is an extension of your API. Rather than calling out to your server, you're calling out to a local file, so we don't have to deal with network traffic or online-offline situations. But really, they should simply be an API interface to your main thread where you can offload something, continue on working on whatever else the main thread needs to process, and then simply asynchronously handle any sort of callback data that comes back. For that then, let's take a look at one of the options for simply polling data and utilizing that to update our front-end display. In this case, our HTML is basically the same, except now that we've learned that utilizing workers to calculate our sum is inefficient, I've removed that option. But otherwise, if we look at our JavaScript, it's still very much the same. Our calc function is identical, as is what happens when we click our control button. However, now we're going to initialize a different kind of worker. You can see here that we've named this method setUpPolar, and what this will do was simply initialize a worker from the worker2 JavaScript file. And then when it receives some data from that worker, it will update that input where we originally had 100,000 with a new number. Obviously, normally this would be something where you might be updating user data in the background or any other sort of occasionally or periodically changing data that you want in a poll method if you can't use WebSocket or some other real-time technology. Later in the course, we'll look at incremental loading and simply pulling in bits of data at a time as they change. And that would be a great time to implement something like web workers that can operate in the background without interfering with your main processing. So our worker in this case is also very simple. You'll notice that we don't even have to set up the onMessage handler since we're not requesting any data from the main thread. However, notice that whereas in previous times we would have used the jQuery get Ajax simple method, we're reverting back to our simple XHR request object and doing this very manually. This is because workers don't have access to those main global variables that have all loaded on the window global object, because again, we're in a separate global instance. There is a method called import scripts that you can utilize to load in some scripts. However, it is very restrictive, and since you don't have access to the DOM, loading in a full library like jQuery not only doesn't make sense, but will actually error out because jQuery on load tries to confirm that it has access to various bits of the DOM. You can see, though, that our pull method is very simple. We simply set it up, tell it that we're going to get some JSON back, and then post the message of whatever the value property is inside that data, and then set up ourselves to pull again in another 5 seconds. And all we're doing here is querying this data.json file, which is periodically being updated with a new value, so that when we load the page, you can see it actually change as we go. So if we load our HTML page again, you can see we're pulling in this data.json, which simply has a single value property. And every time it changes, we get that data. And again, remember, as far as the main thread is concerned, this is just data coming from anywhere. You could be loading it from a server, you could be loading it from a file, you can be generating it dynamically. It doesn't care. In much the same way that we try to build our server APIs in a way that the front end doesn't need to care or know about the logic internally, so we want to write our workers in such a way that the main thread doesn't need to know about the internal logic going on, and we can actually update and improve that internal logic without any detriment or breaking of the front-end main thread. That's a quick introduction to web workers and some of the cases where they're both useful and maybe not as efficient as we might want. For this video, we're going to be talking about the browser paint cycle, which is how the browser handles taking in the data from the DOM tree and constructing the actual visual appearance that displays on the screen. There's two primary steps for this, the reflow and the repaint. These obviously happen initially at the very beginning once the DOM tree and all the CSS and assets have loaded, but also anytime the user interacts with the page in any way or additional data or changes are made. The first step is a reflow, and this happens anytime there's a positioning or sizing change, or really anytime one or more elements move on the screen. So this could be because some element has either changed in size or positioning. We could have added a border, margin, or padding, or even window changes, such as resizing or if the user scrolls through the window. A repaint then occurs anytime there's any sort of visual change. So this not only includes all the times that a reflow has happened, but also if there's any sort of coloring, opacity, or visibility changes. One of the important things to know when you're going through this process is the difference between something like display none and visibility hidden. Display none actually removes the element from the render tree itself, so it has no impact on geometry, positioning of other elements, etc. In contrast, visibility hidden simply removes the actual display of that element, but all the geometric impact that it has on the rest of the surrounding element still applies. With that in mind, let's take a look at some guidelines and goals to strive for as we work through optimizing our site with regard to the paint cycle. The first and most important thing to know is that we're really aiming for less than 10 milliseconds per paint cycle. This is because you have about 16 milliseconds for each monitor frame. Monitors in general refresh at about 60 frames per second, and so keeping our cycles under 10 milliseconds means there's no lag or jerkiness as the browser updates. Really, under 16 milliseconds is the key, but we strive for under 10 because obviously different browsers will render at different speeds. And especially once you start to get to mobile, if it's over 10 milliseconds on desktop, it's definitely going to be over 16 milliseconds on a mobile browser. The next thing to keep in mind is less is better. The less that the browser has to process and reprocess during any changes, the more efficient it'll be. A shallow DOM tree means that there's less cascading impact. A single change to a node, if it's part of a huge tree branch that's got several nested nodes within it, the browser has to reprocess all of those nodes to understand what sort of positioning or other sort of stylistic changes might have occurred. In contrast, if it's a relatively shallow tree, because most of our styles cascade downwards through the tree and not across to siblings, we don't have to worry so much about the residual impact, and the browser is able to use cached processing and reuse rendered views rather than having to recalculate them every time. The next rule is make class changes as specific as possible. But what I mean by this is not to have hugely nested rule sets with 4, 5, 6 different selectors and definers the browser has to process through to find a specific matching element. In fact, that's the opposite of what we want. As a general rule, the fewer selectors you can use, the better, because it requires less CPU processing time. What I mean by specific as possible is that you want to apply the class name as close to the target that should actually be styled as possible. This is because if we change a class name on, say, the body element, the browser has to go through and reprocess every single node inside the body to see whether or not its style should change thanks to that new parent or ancestor class. In contrast, if we apply that class to the node itself or simply one or two parents in order to style an entire module, the browser only has to reprocess the few nodes that are inside that one element rather than, again, the entire document. Another thing to keep in mind is that if an element is going to be changing frequently, particularly if it's going to be animated or moving in any sort of way, taking it out of flow can be key. We do this with either position fixed or position absolute. And the reason for this is, again, we have these reflows that happen anytime an element moves. But if an element is out of flow, meaning that its own positioning, sizing, etc., don't affect the rest of the elements around it, when it moves, the browser only has to recalculate that element itself and potentially any elements that it either covers up or slides underneath, but not the entire document as a whole, simply because one element has moved. The next key thing we want to remember is to cache computed values. These could be things like offset or scroll, anything where we have to ask the browser to compute the certain positioning or offset of either the window or a specific element. The reason for this is browsers are usually pretty smart, and so they will try to queue up multiple changes that would require reflow or repaint, and then apply them all at once, leaving you, of course, with only one reflow and repaint rather than tens or even hundreds. However, as soon as we ask for any of these computed values, the browser has to flush through that queue and process all of them so it can give us an accurate value. We'll see in the next video as we run through a couple tests and look at our timeline that if we're caching those values, we're able to make several changes with only one reflow, and it's extremely more optimal and efficient to do so that way rather than asking for that offset or scroll value on every iteration. Finally, while the browser of course is pretty smart and will try to queue up some changes, as much as possible you should do some of that thinking for it and try to make all the changes at once. Most specifically, this means use classes whenever possible. Classes are the easiest way to apply multiple different stylistic changes all at once. If you can't use a class because it's a dynamic value or you need some sort of calculated property within there, try using the CSS text property rather than the individual style elements. If you're not familiar with it, CSS text contains the actual string that would display inside the style attribute. This allows you to set multiple values all at once and set the whole style block rather than one at a time by using element.style.left, for example. And then finally, whenever possible, make your changes outside of the live DOM. This could be using a document fragment or using a cloned node and swapping it in for the live element once you've made all your changes, or even the shadow DOM, which we'll talk more about later in a different video. All of these options allow you to make multiple changes all at the same time and then apply them in just one reflow and repaint rather than incrementally making those changes and forcing the browser to recalculate several times over. Those are some general guidelines to keep in mind while you're doing your optimizations. In the next video, we'll take a look at some of the impact and how you can actually see those play out inside the browser timeline. In this video, we're going to be taking a look at some of those guidelines that we talked about in the last video and how they actually impact our web app's performance. As well, we'll see how the Chrome Developer Timeline can help us debug and realize what's going on inside those events and the various different functions to help us better optimize all of our code. So for this, we just have some basic HTML. You can see a couple of classes and CSS attributes that we'll get to in a second, a button to help us reset any manipulations we might have done, and then a couple buttons to fire off our events. The main piece we want to look at here is down in our JavaScript, in which case we have a few helper methods, one to move an element, one to set a class, and then again our reset method to undo any DOM manipulations we've done so far. And then we want to take a look at our first two move methods. As far as our user is concerned, each of these methods do the exact same thing. They both move an element a certain amount to the right and a certain amount down. And they both accomplish this by running a loop 10 times, each time moving that element just a little bit to the right and just a little bit down. The only key difference as far as we're concerned is that in our control move, in each iteration of our loop, we're using this .offset left and .offset top as part of our calculation for where the element should be moved to. And in contrast, in our cached move function, you can see that we only grab it once, and then we update just those stored values based on any movement that we've done. What you might remember from the last video is that using these offset left and offset top properties requires the browser to actually go through all of its calculations, flush out any repaints or reflows that it might have had queued up. And so because we use it in every iteration of the loop, we'll see that this runs significantly more slowly than it does when it's simply cached like we have here. To test this theory, let's flip over to our browser. And you can see here again we have our two buttons. So we'll start recording events. First we'll run our control move, then we'll reset it. And now we'll do our cached vals, reset. And now we can see all of the events that Chrome DevTools has given us. As you'll notice, there are literally hundreds of events in here, and it can at times be difficult to find the exact ones you're looking for. There are a few handy ways that we can filter this. We can either use the drop down to select only those greater than 1 millisecond, which pretty quickly gives us our first event right here. Unfortunately, while that lets us find our event really quickly, you can see that when I expand it, that filter is still applied, which means that any sub pieces of my timeline or the function that's being called, if it's less than 1 millisecond, these won't be rendered here either. While this does confirm that this one took 7.4 seconds, if I scroll down a little bit, here's our reset, so we'll skip that. And then our next click was only 2.1, over 3 times more efficient to use our cached values rather than computed values. While that's helpful, because of this filter, I still can't see exactly why. So we're going to go back up to this first click event, and we're going to remove our filter. That will show us everything. And we'll scroll back down to find it. And here we can begin to see why now our function was so inefficient. Notice just how many times recalculate style and this layout method are called. And anytime you see recalculate style and layout, that's a good sign that the browser has to reflow or repaint as part of this method. And obviously, it's going to have to do so at least once because we're moving an element. But we want it to only do so once, as opposed to the several times that you can see here. In contrast now, let's scroll down to our controlled click event. Again, here's our reset. And if we expand this and look in, you can see only one recalculate style and really only one layout. It has a few pieces nested inside it, but functionally only one recalculate style and one layout, which is exactly what we'd want for something like this. And again, 7.4 milliseconds is hardly something that's problematic if that's the entirety of the manipulations that we're doing. But something like this is likely going to be part of a greater control or change that you might be applying. And it also is something that as your app begins to grow, things naturally just become a little less inefficient as there's more memory being used and more changes being applied all at once. So we certainly don't want to be taking up over half of that desired 12 millisecond range just on something that's moving a small text block. So that's the impact of computed values. Now let's take a look at moving by class versus by style. So if we look at our code over here, you can again see that we have two different methods, both of which, according to the user, are functionally the same. But from our perspective, we'll go about moving or styling the element in very different ways. This first one, style move, uses all the properties on the wrapper.style object. You can see we set it to 100, 100. And you can see that in here, basically what we're doing is moving it down and coloring it, and then bringing it back and nulling all those out, moving it down, back and forth. And this time we're doing 11 iterations just so that at the end we can actually see these style changes have been applied. So visually from our perspective, we can tell it's done. You will note in this case, I am actually asking for offset left as part of every loop. This is in fact to force the browser to do a repaint. So just as we just saw that that's negative on performance, in this case, I want to do that. That way I can confirm that any potential speed difference is based on the class moving versus the style moving and not based on anything else that might be going on. Obviously, in a production code, you would want to remove this, but this does help highlight any differences that there might be between the two methods. The by class method is significantly simpler. Again, we're just looking at even or odd and either applying or removing this class moved, which as we saw at the top, applies the exact same styles that we were applying in our style function. If we flip back over to our browser, and begin recording again. First, we're going to move by style, and we'll reset it. Then we're going to move by class, reset. In this case, because all we want to do is compare the top values, I am going to go ahead and do a filter. This time we're actually going to do 2, and just filter straight down to the click events. So you can see here our style method took us 6.5 milliseconds. Again, not too bad, but in the grand scheme of things, not something we really consider optimized. So if we flip over to our browser to see what that looks like, start recording events. First we're going to move by style, reset, then we'll move by class. Go ahead and pull this down. And this time, because we only care about the actual time for each one, and we're not concerned about the individual repaints inside, because we're using offset left, that we know that both of them are going to have far too many repaints, I'm going to go ahead and just filter down to our click events. So we can see here the first one took about 8 milliseconds, and then our class was almost 7. So not a huge difference, and this is pretty standard. Again, we're skewing our results a little bit by using offset left. And even though that does help us see some of the difference because it's forcing the browser to apply the styles based on either the style property or the class name each loop, it does also hurt us a little bit. But this does showcase how moving that element or styling it versus the style object versus the class is slightly less efficient to use the style property. And even as simply a developer, I'm sure you can look at that code and understand that it's a whole lot easier and cleaner to apply it by the class instead of by the style object. So that's a quick overview of how some of the guidelines that we talked about in the last video can be applied and tested both in your code and inside the Chrome developer tools. For this video, we're going to look at a different aspect of DOM manipulation, which is where we're adding nodes to a specific element and looking at some of the different ways we can do that. In this case, instead of our nested text paragraph node, we've replaced that with an unordered list that we'll then add list items to. We have 3 basic ways we can do this. Either what we have here is our control, where we're adding on to our HTML text with each iteration. Our second method, where we create just the string and then set it all in one single go. And then finally an option where we clone the original node, modify the inner HTML of that element on every iteration, and then simply swap the 2 out at the end. In each case, the way we're developing our element is we're utilizing this template, which is simply an li element with a class that will end up either being even or odd, and then the index, 1, 2, 3, or 4, etc., plus element. And you can see here exactly how we're creating the actual HTML string that gets generated. When we flip over to our actual view then, we can go ahead and start recording. We'll do our control version, reset that. We can use our HTML text, reset, and then our clone. And once again, we're going to filter down to all our greater than 1 millisecond options just to clean this up a bit. You can see our first click here took us just over 11 milliseconds. Obviously, again, that's outside our 10 millisecond window. And this is mostly because on every iteration, we're modifying that DOM, so the browser has to go through and do all those sorts of recalculations that we saw before. Matter of fact, if we remove our filter here and we drill back into that specific event, you can see all these parse HTMLs that get executed on every loop that force the browser not only to read in the DOM tree itself, but then reflow and repaint everything. We filter back down to our 1 milliseconds, we can go find our next click option. This, of course, being our reset. And then here's where we use the HTML text. You see, this just took us only 3 milliseconds, just over a quarter of the time of the original, and a huge improvement overall. We're now well under our 10 millisecond window and really don't have too much to worry about. For curiosity's sake, though, we'll go ahead and check out how our clone method applied. In this instance, it took us 6 milliseconds. This is because we're still modifying some sort of DOM rather than simply appending to a string like we were doing before. But because that node isn't inside our live DOM, there's no relayouts that have to happen, simply the parsing itself, until we actually go ahead and use the replace child to swap it in. Depending on what you're doing, sometimes clone can actually be more efficient if you have a lot of more complex changes that aren't easily calculated with simply a string, or if simply for your own development sake, trying to manage everything via a string becomes too complex. A clone node could be a great way to go, which is a huge reason why you want to do these tests on your code itself after you've got the functionality there. Because while our first method, our control, is never going to be the best option, there are instances where you're going to want to have to weigh those pros and cons between inner HTML or a cloned node or some of the other ways that you might go about modifying the DOM. Now we're going to take a look at the impact of displaying or hiding elements via CSS versus JavaScript and the way the browser is able to optimize and handle those. Before we take a look at our code, you can see in our view here I've gone ahead and generated a dynamic list of 10,000 elements, where each one, just like we had before, has both the number of the element itself as well as a class of odd or even based on this template that you can see right here. And then at the very beginning of the page load, I'm simply using our function that we had before to create 10,000 of those items and insert them into the list. We then have two methods that will toggle through either displaying all the elements, displaying just the even, or displaying just the odd. In our control, we're going to use JavaScript. And so when we want to display all the elements, we simply make sure that the style display property is not set or nullified, leaving us, of course, with our default value. If we only want to display the even, then we'll go ahead and loop through all the child nodes and set display either to null for our default value or null if it's not even. And then finally, of course, for odd, we simply reverse our even method. In contrast, for CSS, all we have to do is change the class name of the list element itself, setting it either to even when we only want to display even, or odd when we only want to display odd. And then our CSS here at the very top ensures that anytime the list element has an odd class, all even elements are hidden, and vice versa for when the list element has an even class. To get ready to run our test then, we'll start our timeline and first display just the odd elements. And you can see already that there's a bit of a lag when I push that button. Again, we'll switch to just the even elements, and then go back to displaying all of them. Now we'll go ahead and do the same things by CSS. First displaying just the odd, then the even, and then all. And even that wasn't exactly optimal or immediate, which is a good example of why, no matter how optimal your code is, trying to change the display of 5,000 items at a time is never a good idea, which is why you should always target your code on a very specific section of the window, and certainly make sure that you're not forcing your browser to be modifying huge parts of the DOM that the user can't even see yet, which is why so many infinite scroll type tables and other sorts of elements that are designed to work with tens or hundreds of thousands of rows only actually display and render about 100 or 200, and everything else is simply held in memory. Let's go ahead and take a look at how we did, however. Our first click, which again was our JavaScript hiding all the even elements, took almost 320 milliseconds. It's obviously well outside our window, and actually all of these calls will be well outside our window. We're looking right now simply at relative performance to get an understanding of how the browser handles those two, and again, not so much on the specifics of this particular instance. Swapping it out, we did a little bit better. Obviously, this is because it requires significantly less reflow since we're still ending up with the same amount of elements at the end. And then finally, bringing them all back. Restoring to default state is almost always going to be an optimal solution, and the browser does much better job when there's less overrides rather than more. So the fact that we've now removed 5,000 style requirements is a huge win for us. If we move forward then to making our changes via CSS, we're still at almost 290 milliseconds. Again, this is not a huge change. You'll often see somewhere around a 15% improvement by going with the CSS. As we saw in a previous video, if we had multiple changes, this impact would likely be a little bit greater. Move on to our next click, 230, again a little bit faster, but not a huge win. And then finally, restoring everything. In this case, we actually went up in time. There's no guarantee that one or the other is going to be faster. Just like we've seen in some of the other videos, this is why you always want to run your own tests. There's obviously best practice. My experience, CSS is almost always the generally better practice. There will be instances like this where there's simply so many elements going on that the browser is going to hang up no matter how you do it. And you really want to focus your optimization somewhere else first and then come back to these micro optimizations at the end once you have your overall performance already pretty close. For this section, we're going to be talking about various user experience enhancements that you can make to help your application feel more performant for the user, even if the code is operating at the exact same speed. These are going to be changes that help your user move through your app more efficiently and quickly, and help make all those changes feel significantly more seamless without worrying as much about the micro optimizations that we looked at in the last couple sections. For our first enhancement, we're going to take a look at preloading, which is the act of loading various data that the user is likely about to want to retrieve before they've actually clicked the button or the action that says they want to retrieve it. In this case, we're going to look at two specific examples. First, images, and then HTML. In this case, both the no preloading or the no preload content and the preloading image or preload content are the exact same files. They've simply been copied to two separate file instances so that the browser doesn't think they're the same and use the same cache for us. You can also see for convenience, I've gone ahead and loaded jQuery in simply because it makes the AJAX calls that we're going to need to be using significantly easier and cleaner to use. In our JavaScript then, we have a couple handy methods and variables that we'll use to set status updates so we can see what our preloading status is, as well as actually display the content that we've loaded. Any link here with the preload class, as soon as we mouse over the element, we're going to go ahead and do an AJAX get on that target element, loading it into our browser cache so that by the time the user actually clicks on the element, we've likely already downloaded the entire file and it's ready to display. Similarly, once our user actually clicks on that tag, we're going to circumvent the usual link property of actually navigating to that and loading it either as an image or as just raw HTML into our content block. What you can see now in the browser is that we just have a couple links and a preloading status bar, and then all of our content will load into this area here. If I load the image directly with no preload, certainly not that long of a load. This is all on a local machine, so we'd expect those network speeds to be significantly faster. Notice how when I go to the preloaded, it goes ahead and immediately does that load for me. Obviously with network fluctuations, in this case it took 31 milliseconds, but the file is exactly the same. And what I really want to draw your attention to is this from cache. Again, because we're dealing with local networks here, the exact speed is not as important as the fact that we're able to load this from our cache and have it ready and at hand, rather than waiting until they've actually requested it. This is great for images. We can also use the exact same principle for HTML. You can see here with no preload, it took about 38 milliseconds. And second, again, we've loaded it from the cache, and this time you can see a pretty significant speed difference. Preloading as a technique is something that can be easily applied to things like links as you see here, where you know exactly what the user is likely to do as soon as they've hovered over it. It's also something, however, that you can apply once you begin to understand your user's data and the way they tend to flow through your app in such a way that if a next view is very logical and common, you can go ahead and preload that without any user interaction at all. Changes like that are obviously highly dependent upon your individual application, but it's once you start using preloading in those scenarios where you'll be able to see the biggest changes and overall user experience enhancements. The second technique we want to look at for user experience enhancements is called assuming success. This is a process whereby any calls that you make to the API that involve data changes, rather than waiting for the API to return with a response saying that everything was stored correctly, as soon as the user clicks the button or says that they want to save that data, you go ahead and assume that it's successfully been done, allowing the user to continue on using your application however they might want to. And only in a case of error do you display that notice and take the user back to where they were previously working. For many of you, this may seem counterintuitive and actually against what you've probably been taught as good programming principles, because you're allowing an error to potentially propagate forward into time and potentially even have to roll a user back a couple steps. The difference, of course, however, is that most of the programming principles you've been taught and thought about are for when a machine is processing your code. What we're talking about is for when a user is interacting with your actual application. And of course, hopefully, well over 99% of your API calls should result in a successful situation, provided, of course, you're doing valid client validation and other sorts of techniques on the front end to make sure they can't easily send erroneous data in the first place. That said, like most of these techniques, you will want to use this in places where it makes the most sense, and for highly mission-critical information, where your user's sense of security that everything is fully stored might actually outrank the speed or efficiency with which they can use your app. Sometimes not assuming success and actually waiting with a loader or some other type of indicator can actually be more beneficial for your end user. In this case, however, we're going to take a look at the ability to edit some context in a table. Each person has a name, email, and age. And we've created two users, John Smith and Jane Doe. For our purposes here, any changes we make to John will be seen as a success, and any changes that we make to Jane will error out on our API. Each of them have a save button that assumes success and a save button that doesn't assume success and waits for our API. I've also gone ahead and loaded a notify script, as these sorts of inline notifications are particularly useful when you're assuming success, as they allow you to more seamlessly notify the user further on either of previous successes or an error. Our JavaScript then just simply has a couple methods to easily extract values or store values based on the edits we make to each contact, as well as the save row function, which is the core of our assumed success model. For our purposes, anytime a row has the class of editing, we're actually editing that user, and rather than static values being displayed, we have input fields where you can edit the values for each user. The key thing to note here is that if we're assuming success, then as soon as someone clicks save, we instantly remove that class editing and restore to our static values, making it appear as if everything has successfully been saved. We're then mocking out an API delay simply via set timeout of 3 seconds. Obviously, you would normally hope that your API responds significantly faster than this, but a delay like this helps demonstrate the value of assumed success versus waiting for your API response. Again, you can see that if we're on a successful row, we'll display our notification. And if we haven't already removed the class, we'll go ahead and do so now. And then in an error context, we'll display an error notification. And if we have already removed the class, we'll go ahead and add that class back, allowing the user to try again. Obviously, in this case, trying again is worthless since we have one person who will always succeed and one who will always fail. But obviously, hopefully in your actual application, any errors can easily be remedied or simply just be retried if they failed due to network conditions. Beyond that, we simply use a little jQuery to bind to our buttons inside each row to trigger either an edit or a save. What this looks like in the browser then, is you can see we have two people again, John and Jane. And as soon as we click edit on John, let's change him to have an email at Google. If we click save with assume, everything goes back to normal and I can start go ahead and editing Jane. You'll see after 3 seconds, I get a notification letting me know everything went through. In contrast, if I were to save John back to example and click save no assume, then I don't really have anything going on right now and I just wait for those 3 seconds, making my app feel very laggy and a little bit disjointed. And that would be the case even if it was merely half a second delay. Now, one of the main arguments against assumed success is that error states can feel a little more jarring than they might if you weren't assuming success. And this is true, but again, we want to focus on the 99+% use cases rather than the hopefully extremely rare error cases. In this case, again, we're going to edit Jane's email to Google. You can see that save no assume, which is what we commonly would see. Wait, I get an error, it says please try again. In contrast, if I hit save with assume, everything goes on, it's set to Google. I'm going on my merry way, and suddenly I get this notification. It's not too jarring as I get a notification about my error, and it instantly brings me back to where I was editing so I can try again. Depending on your specific application, you may want to do as we do here and instantly take the user back to the input fields or the data they were trying to change, or you may simply want to queue it up in a message box, allow them to try to change it later. We'll see in a later video as we talk about local storage. That's also a great way to deal with these error conditions. In case the API itself fails, you can save those data changes locally, allowing the user to, again, continue with their assumed success and come back and retry those either manually or automatically, depending on your application at a later date as soon as the network might improve. Those are just quick examples of how assumed success can make your application feel significantly faster and allow your user to move through it much more efficiently and seamlessly without being so tightly dependent on your API or the network or the specific loops of code that might be running on the background. For this video, we're going to be talking about saving and loading data via incremental updates. And what this means is that when we're saving or loading an object, instead of returning all the data or sending all the data that represents that object, instead we're only going to send or retrieve the values that have changed. Now, obviously, this approach requires some coordination with the API development as well to ensure that your API isn't expecting a full object or always returning a full object, and that it's able to handle sending and retrieving partial updates. However, for this video, of course, we'll only be looking at the JavaScript side. Our HTML in this case is almost identical to what it was in our previous example, with the exception of the fact that we've added some data attributes to make our sending and retrieving data a little bit simpler rather than trying to parse out an ID via this name, for example. And then we've also added this button update, which will call out to the server and retrieve a JSON file, in this case either John or Jane, as you can see here. And in this case, obviously Jane is only returning the value that's changed, whereas John returns the entire object, including the email property, which is changed. Our JavaScript then, again, is very similar to what we saw previously, with a couple updates just to make sure that we understand when to do incremental and when not. For example, you can see on our store vals, you have this diff only. And what that means is that we're going to return this object new vals. You can see right here. And when we set diff only to true, all we're going to return are the values that have changed. If diff only is false, we'll return the entire object. And this is how we'll toggle between sending the full object or just an incremental update. I've also created this method setVals that updates both the input and the paragraph tag to whatever data is sent along for this specific row. So then we come down to our save row, and you can see again that we're calling store vals with this incremental toggle, and that will determine what we should be sending. Again, we're using the data attribute ID just to tell us what JSON file we should be, in this case, posting to. And then we'll go ahead and actually post that data. So what this looks like in the browser then, is if I go to edit John, who is not going to update incrementally, and I increase his age, we can see that when I send the data, here down at the bottom of our headers tab, there's this form data, which shows us exactly what data was sent to the API or the server. In this case, you can see I've sent every property on John, even though again, we only changed his age. In contrast, for Jane, let's also make her 1 year older. When I click save, you'll see that because we've requested only the different values, all we sent along was the age. Now again, on a local network with a difference of 1 versus 3 properties, this is not going to make any significant difference. But as soon as you start to hit on low quality networks, especially mobile, as we'll see in the upcoming stages, or with lots of data where a couple properties change versus sending potentially hundreds of different values, this starts to make a significant difference in the amount of traffic going back and forth, which again, especially on mobile, is something that we really want to be cautious about. Of course, we don't only care about incremental updates when sending data, we also care about them when retrieving. So in this case, again, we have our 2 update buttons. And again, as we saw, John will return an entire object, whereas Jane will only return the email property. Now we'll also notice something interesting here, because when I click update for John, even though originally all that would have changed was his email, because we've now also changed his age, that will also update. This is another case where incremental updates can either be a good thing or something that you have to be very careful about. They can be good because it can ensure that the value your API or your server thinks is changing is the only value that changes on the front end. However, if you're not careful and you're not tracking whether or not saves happen successfully on the API, it can also result in some data inconsistency between what's actually stored in the backend and what your user sees on the front end. If I click update, we'll see that both the email changed and our age reverted to 25. And again, this data, which you can see here, is the full object. In contrast, when I hit update on Jane, only her email changes and our age stays at 28 because all we've received back is this email for Jane at Google. That's just a simple introduction to the value of incremental updates and how you can implement them, as well as some warnings about when they may or may not be a good idea for your specific application. For this video, we're going to be talking about utilizing local storage to store any changes to data locally in the user's browser, as well as when we send it to an API. That way, if there's any errors on sending, we're able to maintain that storage even in an offline state. In this case, our HTML again is basically identical to what we just saw in our incremental updates video, with the only addition of the fact that I've added this local forage library here. Local Forage is a library produced by Mozilla that provides a unified API across for storing data locally in basically every browser that supports it, so Chrome, Firefox, and some of the latest versions of Internet Explorer. Likewise, our JavaScript really hasn't changed all that much, other than the fact that when we go to save the row, we're going to use this localforage.setItem method to store our data in that local storage library. You can also see that I've added an error handler for when we're saving our data. This is because we now have one additional row called Jimmy that doesn't actually have a related JSON file and will error out every time. You can see here that inside our error handler, the first time it goes through, we're actually going to retry. And this is a pretty standard practice anytime you're working with offline data or flaky network connections and want to utilize something like local storage, since it allows you to retry saving that data to the API just in case there was a temporary network glitch. But if we fail twice, we're going to assume that the connection itself is bad, or potentially there's something more permanent going on with the API. So the HTML in this case is going to be pretty boring. There's actually nothing we can really see going on the front end when we're storing our local data, which of course is exactly the point because we want this to appear just as seamless to the user as possible. If I edit something that's going to succeed, we get our standard success message. If I edit something that won't succeed, change his age to 29, we're unable to save your data for Jimmy, very sorry. And then on the second retry again, we've assumed that there's something permanent going on. So we're going to just tell them to wait for later. Now, right now, because all we've done is save the data, if I refresh the page, we're back exactly where we started. However, in the next video, we're going to take a look at retrieving that data from local storage, allowing your user to really begin to work entirely offline and only send those updates when the internet comes back. So in the last video, we took a look at utilizing local storage to save data locally when we're trying to make updates to our API. In this case, we're going to take a look at how we can utilize that on load to retrieve those values and allow our users to actually fully work offline. In this case, our HTML is exactly the same as it was before, but I want to remind you of two quick things. First is that John's age, according to the API, is 25. That's what we retrieve from the server. And Jimmy's age is 30. And this is important because in the last video, we changed both of those. And you'll remember we stored those changes locally so that John became 26 and Jimmy became 29. Now, our JavaScript again is almost identical with the addition of one method, and that's this load from local. And what this does is iterate over every item that we've stored locally, find that row based on its ID, and then call setVals with the data associated with it. And then the one other change we've made is that setVals now returns this Boolean changed to let us know whether or not the values that were stored locally are the same as what we retrieve from the server, or in this case what's in our HTML, or are different. And if it's changed, we're going to go ahead and call saveRow on that row. And what this allows us to do is if the user is offline and makes several changes, then the next time they load up our page and are online, we'll instantly send those changes that they previously made offline and had stored locally back to the API to ensure that our data is consistent and that data is stored as permanently as possible, as quickly as possible. As soon as the page is ready, we go ahead and call that load from local. And what this means is we'll flip over to our HTML is that as soon as I load the page, you'll see that not only has our HTML updated to reflect the new ages for both John and Jimmy, but you can see that we've also saved the files for both Jimmy and John. Now, of course, Jimmy still doesn't exist, so we're still going to get that error. But obviously, in a real-world application, hopefully by this point, you've either fixed whatever is going on with the API, or it was simply the network conditions originally, and if the user has loaded it up in better network conditions, these saves now persist. So that kind of brings together a wrap of what makes local storage so powerful and so useful for your end user, as it allows your end user to continue working even in poor network conditions, or even worse, if your API itself is actually failing for a while, and still make their changes and store them, and see those reflected changes in their app. Now again, the only reason they can see those reflected changes is because of the assumed success model we took before, where we're willing to save these things immediately, and even in the case of an error, allow the user to keep going, and then only later, if that error appears to be a permanent situation, call that back into focus and give them a chance to try again or to change it. For this video, we're going to be taking an overview look at the AppCache and our cache manifest, which allows us both to run an application offline, as well as significantly increase our load speed for future loads thanks to having most of our files already cached and ready to use. Now, AppCache itself is a huge topic that requires a lot more study than simply one video. So if you want to learn more, I highly recommend this site here, which is appcache.offline.technology, which has a great list of basic facts to get you familiarized and started with AppCache, as well as several resources here down at the bottom to take you deeper into AppCache and show you some of the nuances and tricks to making it work best for your specific application. For our case, however, we're going to take a look at just a very basic manifest. You can see here that I've named this manifest.appcache, and that's a pretty standard recommendation. You certainly want to be ending it in .appcache or potentially .manifest. The basic format of a manifest is relatively straightforward. The only hardline absolute requirement is that the first line must be this all uppercase cache manifest that you see here. After that, anything that starts with a £sign like this is a comment, so it won't be parsed by the browser. However, it is highly recommended that you use this sort of versioning for reasons that we'll see later as far as updating your actual application goes. After that, there's three primary sections. The cache section, which is actually the default section, so we could remove the signifier if we wanted to. But inside this, we designate the files that we want to be stored in our cache. You'll notice here that I've only included the JavaScript files and not the HTML. And that's because any HTML file that references this cache was automatically included inside the cache and doesn't have to be explicitly listed inside your manifest. Some people say that you should, some people say that you don't need to. It's entirely up to you. As far as the browser is concerned, it's the exact same scenario. Our next section is this fallback section, and this is how we tell the browser what to load in the case that it can't load certain other assets. So you'll see here in the HTML in a moment, I've required this online.js file. However, I haven't stored it in the cache, which means that as soon as we're offline, it can't find it. So this fallback section says, if you can't find online.js, load offline.js instead. And then finally, our network section. This is one of the major gotchas of AppCache that if you're not careful can be very confusing. Without this network section, anything that's not defined inside the cache won't be loaded at all, even if you're running online. This means is that any images or external sources, if you've loaded it up from the cache and you can't find it in the cache, will simply be essentially 404'd and reported back to the browser as unavailable. What this network section allows you to do is either specify specific files that you do want to load from the network anyway, or in this case, simply use a wildcard which loads everything that's not specified inside the cache via the network as normal. So that's the basic manifest. Let's take a look at what has to happen inside our HTML for the browser to know to use it. It's actually very simple. All that's required is that we add this manifest equals and then the name of our manifest file to the HTML node. This tells the browser to look for a manifest file as soon as it starts parsing the HTML. Outside of that, the only other changes that we've made for our HTML are a few CSS changes for when we're offline, just so we can let the user know. And then down here at the bottom, again, like I said, we're requiring this online.js file. One thing to note is that in this case, we're still loading all of these resources from external domains, which means that if we were truly offline, none of this would work. However, in this case, since we're simply doing this for demonstration purposes, all we're going to do is kill our server to emulate being offline, so these resources will still work. In an actual app, you would of course want to download these yourself. There are some ways for non-SSL apps where you can cache external resources straight from the domain. However, in any SSL app, there is still a same source policy for the manifest. So all of these would actually have to be loaded into your server and your resources and then downloaded for the manifest from there. Next, let's take a look at our online.js file, which as you can see is an extremely simple way of setting a global variable online state to either online or if we're using our fallback, offline. This will allow us inside our AppCache.js file to have an easy variable to use to monitor whether or not we're online or offline. Obviously, in a production app, you would likely want to do this a little bit more dynamically with some sort of timeout or interval check to see if you've come back online, or a few other ways that we'll actually look at in a later video when we're talking about intermittent networks with regard to mobile optimizations. Once inside our AppCache.js file, we've really only made about 3 changes, all of them relating to this online state variable. The first is that when we're saving a row, if we know that we're offline, we just go ahead and return, as there's no point in trying to do a post and warning the user yet again that we failed to save it when we already know that. The next is inside our load from local, where we're doing the opposite. If something has changed locally and we're back online, we're going to go ahead and try to save that row. And then finally, when we initially load our application, if we're offline, we're going to both notify the user as well as add this class offline to our body element, which is what allows for those visual changes. So if we flip over here, and then we go ahead and load our page. Now you can see it looks pretty similar, but if we open up our console, there's a few things to note. Chrome will tell you that it's both creating the application cache and then progress you through several events that happen inside the application cache. These events all happen when you're first loading a manifest for the first time. So it will check, download it, and then iterate through all the resources, both our JS file and note that offline JS was downloaded. This is important because even though our HTML didn't require offline.js, our manifest did. And so it's gone ahead and downloaded that already. That way, as soon as we go offline, we're still getting the right results. So with that, now let's go ahead and kill our server. We can reload the page. You can see that we've got our warning. We now have a little offline status. And in the console, you can see that rather than creating a cache from the download, we're just loading it from this manifest. It's checked. Naturally, it can't load the new manifest since our server is offline. But we can still go ahead and update our ages or change Jane's email. And all these things save and operate just as they would when we're online, except of course none of it's sent to the server. But I can still reload the page again, and thanks to our local storage that we implemented last time, all these changes have persisted, and as soon as the user comes back online, those changes will be sent back to the server for permanent storage. So that's just an example of how you can use AppCache to allow your entire application to run offline, and combined with local storage, allow your user to still utilize and make changes while offline to be actually persisted later with very little overhead or limitations for your end user. For this video, we're going to take a look at some of the tools available for debugging and benchmarking your web applications as seen via mobile. There's a couple different ways you can go about this. Both Android and iOS support what's called remote debugging, where you can utilize the web inspector tools that we've seen already in all our previous videos, except execute all those tools as if they were on your mobile application or your mobile device as opposed to the desktop like we've seen before. I'll walk you through this with Android as it's a little bit more established, but iOS does support many of the same tools via Safari. To get started with remote debugging for Android on Chrome, I highly recommend this site here, which will walk you through exactly how to set up your phone. But as an overview, it simply requires connecting your phone via USB cable to the computer you want to do the debugging on, enabling USB debugging on your phone itself, and then opening up this Chrome Inspect tab inside your Chrome browser. You can see here that it's found my Nexus 5, as well as the 2 tabs that are currently open on it. With that, I can basically remotely control my phone. You obviously can't see this, but it's simply flipped over the tab. And then I can click Inspect, which brings up these same tools that we've seen before. Both the element, our network tab, the timeline, all the same tools that we used previously are now available to us here. In addition, since oftentimes trying to go back and forth between two screens can be somewhat challenging, there's an item here that looks like the little phone that says Toggle Screencast. As soon as I click that, you can now see my mobile screen and actually even interact with it. Here I'm actually using the mouse to scroll. I'm not doing anything on my phone. Or I can even scroll down and use it to click and emulate various touch events, such as highlighting the bar, even running these tests again. This also highlights an important feature that we often forget about, which is that all those same benchmarking tools that we used for our desktop web are all simply websites, which means we can still load them on our mobile device and run tests just like I've done here to re-emulate the various local optimizations, loops, etc. that we looked at in some of our previous stages. So that obviously allows us to see the device itself, and for Android with Chrome, that works very smoothly in much the same way that an iOS device on Mac will also work very smoothly. But sometimes you don't have access to that exact lineup, or you're not able to plug in the USB, or you have multiple devices that you want to test at once. For this, one of the best tools is called JSConsole.com. And what this allows you to do is remotely control any device or any web page via an online JS console. So you can see here, it's just JSConsole.com. And then all we have to do is type into it this :listen, and that initializes a new connection for us. Once we've done that, we can simply paste this script tag into our file, like you see here, and that allows us two-way data access back and forth, both for retrieving console logs, like you can see here. This line itself simply comes from my JS file right here that says loaded remote file. But I can also send messages back. So for example, if we pull up our inspect again and focus the other tab this time, where I've loaded my local item, and let's go ahead and inspect it. You can see here, I have a page with two columns. Now you may have noticed in our JavaScript, I created two methods, stack and columnize. These simply add or remove the class column to take these chunks of text and either stack them on top of each other or columnize them and put them next to each other like we see as default. Now I'm going to go ahead and make this stay on top so that when we load open our remote console again, so then I can type into here, stack, and you can see that it executes it, and those changes are reflected here, where I can then scroll through and see the two columns are stacked again. Or I can type columnize and take it back. These two tools combined allow me to use my standard inspector tools for the timeline, my network tracking, and basic console access when I have direct access to a device, or JSConsole.com when I only have remote access to a device, are great ways to bridge the gap between our mobile development experience and our desktop development experience, and bring those together in a way that we have all the debugging tools and access that we do when we're on our desktop, but still testing and optimizing for a mobile device. For this video, we're going to be talking about different ways to conditionally load assets. The reason for this is that oftentimes when you're on a mobile network, you want to be highly conscious about the data you're transmitting and specifically how much of it you're transmitting. And so what we're going to do is build as if we're on the mobile network with the minimal amount of data requirements necessary, and then extend upon that if we're on a desktop situation. To do that, we'll look at both style sheets, JavaScript, as well as images that can all be loaded conditionally based on, in this case, the type of device that's accessing our site. For this, we're going to be using a couple different technologies, the first of which is a JavaScript plugin known as Conditionizer, as well as a mobile detect script that we'll utilize to tell us whether or not we're on a mobile device, such as a phone or tablet, or on a desktop. Obviously, these days, we often want to focus on feature detecting rather than device detecting, which for most cases is exactly what you want when you're trying to decide whether or not to allow a user to do something. But because in this case, what we're really trying to tell is exactly what kind of device they're on so that we know how careful do we need to be with their data, we're going to instead use a standard device detection. So we'll return back to the HTML in a moment when we want to take a look at some of our images. But first, let's go over to the Conditional.js so you can see how you can utilize Conditionizer to only load the assets that you need. So what Conditionizer allows you to do is easily add tests for anything that you want to configure. In this case, I've added a test called desktop, which uses our mobile detect script and then returns the inverse of whether or not we're on mobile. And then we're able to configure our conditionizer with a series of tests. And what this says is take the test desktop, and if it returns true, look for the script desktop.js and insert it. Look for the style, so desktop.css, and insert it, as well as add the class desktop to our body element so that we can use those styles as well. You can use as many or as few of these for each of your tests as you want. And you can also use a whole suite of tests depending on how much you want to personalize to a specific browser or other sort of condition. You can see here that our desktop CSS is very simple. All it does is remove anything that says mobile only, display the desktop only, which we've previously hidden inside our HTML, adds a little bit of styling to our info and paragraph tags, and then also brings in a media query to limit the size of our image. Desktop.js is even more simple. All it'll say is that it's loaded on desktop so that we can easily see that. So when we pull this up in the browser, you can see that we have our conditional assets. It's displaying on desktop, which is powered by this desktop only span, as you can see right here. And of course, our mobile has been hidden thanks to the styles we brought in via desktop.css. In contrast, however, we want to take a look at how that would appear on our mobile phone. We can pull up the handy debugging that we talked about last video and inspect that and see that this exact same page, when displayed on mobile, has none of the styling for the info tag. Our mobile only is displaying exactly as it should, and none of the desktop elements are there because we haven't loaded those assets. You might also notice, however, that the picture has changed. And this is something that even beyond simple mobile detection can be extremely powerful and helpful when you're trying to control data, especially considering how much of the data that we use is often transmitted via images. So let's go back to the HTML. And you can see that we've included this picture element. Now, picture is a brand new tag in the HTML5 spec, and if you're going to be using it in a production app, you likely will want to polyfill it with something like picture fill. But for our purposes here, since we're simply operating in Chrome, which has full support for the picture tag, we can simply use it as is. Now, the way the picture tag works is it first requires some image tag embedded inside it. And this will be whatever the default is if for some reason either none of the sources above match the required rules, or it's often used as the fallback in a browser that doesn't support this type of conditional image loading. For the images themselves, though, when we want to choose what to make available, we use these source tags. And you can see here on the first one, I've included a media attribute. And this is a standard media query, just like you'd see in the CSS. And in fact, it matches our desktop.css media query exactly, limiting it to when our viewpoint is 800 pixels or higher. In that case, it will use the source of desktop.jpg. For our second source, because there's no media query at all, this will match anything, and we set that to our mobile.jpg. And then what the browser does when it encounters this is it walks down each of the source items until it finds a match. So on our desktop view, because our viewport is greater than 800 pixels, it recognizes that and loads the desktop.jpg. For our mobile, however, as you saw, the width is too small, and so we've loaded a separate image, in this case the mobile.jpg. And obviously you can use this to either load a completely different image, as I did to make it clear, or simply a different resolution or quality of the image to take more care of your user's data. This can also be useful when you're working with retina displays or any sort of display where the resolution is different. You can customize the image to match the user's resolution. Now, this is how you can handle explicitly setting which image you want to set. There's another version that embeds the source set elements on the image tag itself and allows the browser to more algorithmically pick it for you. This can either be great or awful depending on how much control you want over the situation and how seamlessly you want everything to responsively adapt to the user's individual devices. Embedding the source set and using another attribute called sizes on the image itself is significantly more adept at basic responsiveness. However, it's not as good when you're trying to do something like this and manage explicitly the amount of data and the quality that you're trying to send along when your focus is actually on data usage optimization rather than simply the particular cropping or sizing of an image. For this video, we're going to be extending upon our previous offline application where we were using AppCache and local storage to begin dynamically monitoring whether or not we're online or offline. This is particularly helpful when you're working on a mobile device where the network likely could go in and out, or anytime really someone is on an unstable connection. For this, we're going to utilize the offline JS library provided by HubSpot, which monitors all your AJAX requests, and as soon as requests start failing not because of a server error, but because of a request timeout or other sort of loss of network connectivity issue, it both offers events that you can hook into to notify your user or begin saving all your data locally, as well as queuing up all those AJAX requests so that when you come back online, you can instantly replay them all. What this means is that our HTML is almost identical to our AppCache from the last video, other than the fact that instead of loading our own online.js or offline.js, which if you remember simply set the window.onlineState property, now we're going to load our library instead. Our JavaScript as well is largely very similar with a couple key differences. First, you'll see that we've added some configuration for the offline library because we know in our application, the user might have made changes previously, or the user might have made changes previously while in an offline state. So we need to update that data, or potentially it might just be a while until they're going to try to edit anything. And we want to check immediately to see whether or not they're offline. We set this check on load property to true. Also hooked in to a couple different events that the offline library provides, namely up, which tells us when the connection has been restored, and down, which of course lets us know that the connection has gone down. The one other important thing to note is that we've updated our load from local function to accept this for save parameter. What that allows us to do is that when the network comes back up, we can call this load from local with true to ensure that any changes that have been made while the user was offline are automatically sent through to the API. Now, obviously, in a standard application, you'd probably want to do some sort of limited monitoring to make sure that you're only sending these changes if the user has actually done something. But for our purposes, with only 2 rows, it's safe to allow us to just send everything as soon as the user comes back online. What this looks like for our user then, we flip over and we can see that everything is running as normal. We have this light little box here that tells us that we're online. Obviously, you can style this or remove it however you want. But if we go over and we kill our server, and we come back, go ahead and refresh the page. You notice that we seem to have lost network connections. From now on, all changes will be saved locally until you reconnect. And per our previous development, we can go ahead and still change some of these things without any problem. And as far as the user is concerned, they're simply able to still continue doing their work. They're aware that they're offline, so we're maintaining that communication with them. But otherwise, everything is running as normal. And then when we come back and want to re-enable our server, wait for that favicon check to happen again. And as soon as it hits it, you can see that our connection has been restored. All changes are saved to the server. And of course, we've called that load from local to update our API with whatever changes we've tried to make. So that's a very easy to implement way to begin monitoring your network connectivity, and combined with the changes we've seen from AppCache and local storage, allows you to have an entirely functional offline application that your user can use seamlessly no matter how bad their network connection is, while still ensuring that their data remains consistent whenever possible.
As we wrap up this course, let's take a quick moment to do a review of some of the things we covered. One of the first and most important pieces is utilize benchmarking. No matter what kind of code or how experienced you might be with a loop or optimizations or algorithms of any kind, inevitably you're going to want to use benchmarking to understand the specific code running in this specific instance and comparing it both across browsers, across different devices, and specifically across the general span of your user base, whatever that might be. Once you have a good understanding of the basic benchmarking, you're going to want to dig into that timeline so you can understand the browser flow, what's happening as the paint cycle occurs, as the network begins to process, all of these items that might seem small in and of themselves, but over time they begin to build up, especially as you add on more and more complexity and more requests and repaints and reflows and other sorts of additions and changes to your DOM or anything else that's going on within your application. One of the most key things to remember is that there simply is no one magic solution. Just like we saw with web workers and some of the other optimizations, many things that are great in one situation can have no effect at all or even be detrimental in other situations. It's important to understand both your application and your user base, whether that's the kind of browsers they're going to be using, the kind of interactions they're going to be doing with your application, or just the overall understanding of what's most important to those users in each interaction as it occurs. With that understanding comes the recognition that oftentimes you want to make user experience improvements along with raw speed. Again, these are changes that might not actually show up in a benchmark or even the timeline, but they affect the way your users perceive the performance and speed of your application and the efficiency with which they can move through it and get things done. That efficiency, of course, isn't important only in ideal conditions, but also for offline instances or when the network is going up and down. And so for that, we use things like local storage or the AppCache, not only for those flaky network conditions, but also just for basic performance in caching our data, in caching our assets, and other sorts of improvements that make sure the user's experience is as best as possible. Hopefully throughout this course, you've been able to see different ways that we can optimize our users' experience and interactions with the app, both in the raw speed that we implement in our JavaScript, and also in some of the principles and patterns that we put in place to make sure that not only does our code execute quickly, but also the user's experience is as optimal as possible across all aspects of our application. Thank you so much for spending time with me. I hope this was a great course for you.